I want to make a video about how to make a motion diagram for a ball that's thrown up with an initial velocity of 20 meters per second. So I'm going to do this by going from this table here, which the leftmost column in the table shows time, and I'm going to start by talking about what happens to its instantaneous velocity, which is this column here. And over here, where I'm going to draw the motion diagram, and to that purpose I have a coordinate system where the positive y direction is pointing up, and the origin of this coordinate system is at the floor. For my distance, one of these little divisions is equal to 1 meter. You can see that from this scale here, 5, 10, 15, 20. And I'm going to use a different scale for my upward velocity. I'm going to use 1 division equals 5 meters per second. So at time 0, I have an initial upward velocity of 5, 10, 15, 20 meters per second, which is what this magenta shows. And so the fact is that on the Earth, with the acceleration of gravity, the physical fact we have is that every second there is a delta V of what I'm going to assume is minus 10 meters per second. It's actually 9.8, but to keep the math simple, I'm going to use minus 10. And so that being the case, if I have 20 meters per second at 0 seconds, 1 second later, I'm going to add this minus 10 to that to get 10 meters per second 1 second later. And as a result of that, over this first second, I have an average velocity, that would be the average of these two numbers, of 15 meters per second. That means that if my average velocity is 15 meters per second up, and I've been doing that average velocity for 1 second, it means my displacement, my change in position, is plus 15 meters. And so if I start at 0, which is my assumption, I'm going to go up 15 meters. I'm going to go up 15 meters displacement. I'm going to be at 15 meters. And so the motion diagram analog of this is that I draw my ball 1 second later up here, and that I now have a upward displacement of 5, 10, 15 meters, like that. And I start with 20 meters per second, and 1 second later I have 10 meters per second. And I'm also going to document the fact that my delta V during this time interval is minus 10. So that would correspond to a downward vector like this. Okay, stepping 1 second forward again. 1 second forward again, I have another, over 1 second, I have another minus 10, which is going to get me to 0. The average between 10 and 0 is 5 meters per second, which means that my displacement is 5. And so that means I can go up another 5 meters. It's still a positive displacement, which means, of course, up because of my coordinate axis. And so at t is equal to 2, my new position, since I've gone up another 5, my new position is 20. You can see that corresponds to where I am on my scale here. I can't draw a 0 instantaneous velocity vector, which was what I have at time 2. And so I'll just say Vy is equal to 0 meters per second, and that corresponds to the apex. 1 second later, from 2 to 3, I then incur another minus 10 meter per second. And so since I start with 0, I'm now at minus 10. The average velocity of 0 and minus 10 is minus 5. Now my my displacement is minus 5. The fact that it's minus means that it's downward. And so I'm going to move the motion diagram over so I don't have to draw it on top of itself. I have a -5 displacement. And so here I am going from t equals, that's not t equals 0, that's t equals 2, excuse me. This is t is equal to 3 seconds. And so I've gone from 20 to back to 15. And my delta V continues to be down 10, as it is in this interval as well. And then finally, I incur another -10 delta V, so I have a -20 meters per second. The average of -10 and -20 means I have a -15 meters per second velocity, which means over 1 second that would be a -15 second displacement. And so a -15 second displacement of -15 means I come down 15. So I'm going to come down t equals 4 seconds to where I started. There's a -10 right here I neglected to put in. And then, of course, there's the same delta V of -10 here. And if I come down -15, and I was at 15, I'm now back to where I started. Like that. Okay, so through this whole process, I've had a -10 delta V downward, and that corresponds to the fact that I have -10 meters per second, which means I have -10 meters per second. It's constant. That's the acceleration I'm assuming here. And so that's how you generate an accurate motion diagram. You can see that there is a symmetry in the position. I go from 0 to 15 to 20, and then from 20 to 15 to 0 on the way up. I have one sequence, and then the reverse of that sequence is what I get coming backwards. My motion diagram is has a similar symmetry, except that on the way up I have an upward displacement, on the way down I have a downward displacement. These two have the same magnitude, just opposite directions. And every single 1 second interval has very consistently a downward -10 meter per second delta V. Here and here and here and there. This is the equation analog of what I'm doing in the table here. What this says is that my velocity Vy at some time t is equal to the initial velocity plus the acceleration times the time, and so my initial velocity is 20 meters per second, as you can see here and here as well. To put the numbers in there, if I put -10 meter per second in for the acceleration, I get 20 minus 10t. I should also add my last velocity here, which is like this: -5, -10, -15, and -20.